All right, section 3.1, actually chapter 3 in general, is going to start our discussion of whole numbers. In 3.1, we're going to talk about numeration systems and kind of where our number system came from. There's going to be components of this section that you probably haven't seen before. And this section might be the section that people like the least in terms of looking at it and saying, I'm going to use this in my second grade classroom, okay? Part of the point of this section is to make you a little bit uncomfortable and put yourself in the position that the children feel like when they're in your classroom learning how to add or subtract. Okay, so keep that in mind. The point is to feel a little bit uncomfortable because things are going to look different than the number system that you have known for the last, most of you, almost 20 years. Okay, so everybody good at that to start with. So prepare to be uncomfortable. Wonderful, right? Okay, so to start with, our number system is called the Hindu-Arabic numeration system. It was developed by the Hindus and then transported to Europe by the Arabic. The properties in this number system. All numerals are constructed from 10 digits. What's our smallest digit? 0. And what's our largest digit? 9. So we do not have a digit that's 10. That's 2 digits. Okay? So 0 to 9. Place value is based on powers of 10, which is the number base of our system. And it's exponential. Remember that a to the n is a times a times a times a, so forth, n times. That's what it means. So when we have our number system, we have a tens place and a hundreds place and a thousands place and so forth. Those are all 10 to a power. They're all 10 to a power. All right, the first number system that we're going to look at was set by or created by the Egyptians. These are, how many of them? 7. The 7 numerals for the Egyptians. So I'm going to let you draw them in first before I keep talking, because you guys stop listening when you're writing anyway, right? That multitasking thing's tough. Okay, so the numeral and the description go together. Hopefully that helps you a little bit to draw them. The vertical staff, I'm good with that one. I don't know about you. I can draw that one just fine. Heel bone, not so bad. It looks like our intersection symbol or an upside down U, right? The scroll, not too bad. The scroll's an interesting one. They would actually draw the scroll either like this or backwards. So sometimes it was flipped around to look more like a letter P or something like that. It doesn't really have a specific direction, if you will. The lotus flower challenges me a little bit more in terms of my artistic ability. The pointing finger is just funny looking. This next one actually has 3 different names that I've seen in 3 different books that I've used. Sometimes it's called a pollywog, sometimes it's called a fish, a burbo fish, and sometimes it's called whale. So it should look a little fishy like that's what a pollywog is, okay? And then the last one is an astonished man. And I've actually seen, this isn't how every resource for the astonished man especially has drawn it. I've seen an astonished man look like this too. I'll draw it just so that you can see what it looks like. I've also seen him drawn like that. So I think that it must be more kind of like, we think about handwriting, who was the transcriber kind of stuff, and the different, artifacts that have been dug up, stuff like that. But this is another image of an astonished man. So it looks more like a man. Maybe the first one looks more like a woman. I don't know. Each of these have a value in the number system. So the first one, the vertical staff's value is the value 1. It's worth 1. A heel bone is worth 10. A scroll is worth 100. Thinking in terms of patterns, what do you suppose a lotus flower is worth? 1,000. And a pointing finger. 10,000. How about our polywog? 100,000. And I'm convinced that the astonished man is astonished because he's worth a million. I mean, would you not be excited if you were worth a million? Absolutely. There are some definite, like, yay, exciting things about their system, and there are some definite, like, seriously, that's just terrible things about their system, okay? So the yay, exciting thing is that it's really easy to read and write numbers. Like, you can look at it and you'd be like, oh, I know what that value's worth. So let me show you how their system works. Here's their value. There are 3 scrolls, and there is a heel bone. Well, a scroll is worth how much? 100. A heel bone's worth what? 10. So it's very easy to identify and say, okay, I've got 3 heel bones, so we can actually we'll do part C first just so we can get a feel for it. 3 heel bones, so this is going to be 300. I'm sorry, 3 scrolls, so it's 300, and a heel bone, and it's worth 10. So what do you suppose this number actually is? 310. So in this sense, their system is very nice and simple. But if you can imagine writing out the number 99,999, it's not so simple. I mean, it's simple, but it's time-consuming, right? You have to write a lot of symbols. So the questions that it's asking before I just went out of order because it sounded like so much fun, was it asks us what we're supposed to do to write down the numbers before and after this particular number, okay? Now, I don't really want you to turn it into 310 and then go backwards and write 309 and 311. That's not really the point. The point is sort of like to put on your hat that says, I'm an Egyptian, you know, like this. If you're like this, how do you do it? I don't even know. Like this? I don't know, whatever. You're an Egyptian, and you're writing in Egyptian, and somebody owes you this number of whatever we'll say dollars because I don't know what they used, but we'll say dollars. They owe you 3 scrolls and a heel bone worth of dollars. And your question is, if they pay you back 1 vertical staff, how much is left? How much do they still owe you? So they still owe you the 3 scrolls, right? But they don't owe you a heel bone anymore. What do they owe you?
1 less than a heel bone.
1 less than a heel bone. So what would 1 less than a heel bone be? 9 vertical staffs. Now, it's worth noting, just in case you were to see it, this is perfectly fine. They will also stack things. So if you see this done like this, you might see, hang on. Yeah, that was right. Once you get more than 6 objects, you'll see them sometimes stacked on top of each other, like split about half and half. I don't care if you stack them or not, but just so that you know it's the same thing. Okay? So this would be the number that comes before 3 scrolls and a heel bone. What was the number that would be coming after it?
3 scrolls, a heel bone plus a vertical staff.
3 scrolls. Oops, I didn't mean to draw 4. A heel bone and a vertical staff. Okay, so this is the person that borrows another dollar from you. Yeah? Okay, so doing the numbers before and after is not so bad. Changing the digit into our numeration system, also not so bad. Now, it's equally clean and simple to actually take their number and to write it in our number system. I didn't say that wrong. Take our number and write it in their number system is what I meant to say. I have 23,145. And we're going to take each place value and write them because while theirs is not a place value system, this 2 right here means something in their system. It means 2 what? 2 10,000s, and then 10,000 is a pointing finger. So I need 2 pointing fingers. So now you get to test your artwork ability. And I guarantee they're not going to be perfect, but they should be identifiable. Okay, don't make me guess. Is it a polywog or a lotus flower? It's not a good place to be. How about the 3? What is that in the place value of? The thousands, which is the lotus flower. So I need 3 lotus flowers. How about the 1? What is that the place value of? A scroll. So I need just 1 scroll. The 4? The heel bones. And the 5? The staffs. Okay. So it may be cumbersome, take up a lot of space, write a whole bunch or whatever, but their process and their number system is pretty straightforward. Agreed? Okay. Things get more complicated with the next system because their system only has 2 symbols. And that might sound like, well, that's kind of cool. I don't like the symbols. Those were all crazy things I had to draw. But with fewer symbols comes more complication. So the first one looks like, I hate to use the phrasing this, but I know you guys are thinking it. You think it looks like an upside down triangle, but triangles don't really have any direction, but such is life. You probably said it in your head. It's an upside down triangle, didn't you? Yeah. And as we're drawing them, you don't necessarily have to fill them in. If you want to draw them sort of empty as we draw them, I'm okay with that, just for the sake of not having to draw so much or whatever. The second one looks almost like an arrow. Yeah. And as we do that, if you want to draw it like this, so that it looks like sort of the outline of the arrow, I'm okay with that too, just for the sake of not having to shade things in funny and whatever. Okay. They do each have a specific value. The value of the triangle is 1, and the value of the arrow is 10. And here's where the complication comes in. They actually have a place value system. So we have a place value system, and in our place value system we have the ones place and the tens place and the hundreds place, which is 10 squared, and the thousands place, which is 10 cubed, and so forth, right? All powers of 10. But their system is a base 60 system. So that means they've got, just like us, a ones place, but instead of having a tens place, what do they have? A 60s place. And instead of having a 10 squareds place, they have a 60 squared, and instead of 10 cubed, it's 60 cube, and the process continues. They still write it the same as us, with the place value that's the biggest on the left and the smallest on the right. So that part's the same. Okay? But converting in and out of their number system is a little more complicated. So we'll do the next set of questions actually in order instead of out of order like I did the first slide. Consider this value. Triangle, a bunch of arrows, a bunch of triangles, and it asks us the question, what Babylonian numeral comes before this value, and then what comes after? Well, all the triangles are worth 1. So if I take this number and I need to decrease it by 1, it'd be in essence decreasing it by a triangle, right? So what would I have to do the number before? Just take off one triangle. That's easy, right? So let's do that. I have a triangle at the beginning. I have 5 arrows. So none of that changes. And then I have 1, 2, 3, 4, 5, 6, 7, 8. I have 9 triangles at the end. So now how many will I have? 8. Okay, is that all right? Number before is simple enough. Okay, so what would I need to do then if I wanted to add 1 to this system, the number that comes after this one? Add a triangle. Now if I add a triangle, how many triangles is that going to give me?
10.
Ooh, that'll give me 10. But I wouldn't write 10 triangles, right? What would I do? Yeah, I'd trade this triangle, set of 10 triangles, in for an arrow. But I already have 5 arrows. So if I have 6 arrows, how many does that give me?
60.
That's 60. But 60 is my place value system, right? So again, ignore this piece at the beginning. We'll talk about him in a minute. But those 6 arrows would turn into the next place value over. It's like when we add numbers together and we put a 0 to hold the place, and we just add one to the next. We call it carrying, yeah? And we carry it over. Well, we carry it over as 1 because it's 1 100 or 1 1000. Well, here we're carrying it over as 1 into the 60s place. But the 60s place already has a 1 in it because it had a triangle in it to begin with, right? So the number that actually comes after this is the triangle that it started with and another triangle. And there is no other way to write that. So I hope that you're looking at and you say, now wait a minute. Because what does that number look like? 2. but it's not. It's actually 120. Who wants to be accountant for the Babylonians? Yeah, probably not, right? Like, that's confusing. So if you take a look at it, it says, how else could the value be interpreted here? Yeah, it could be the number 2. And depending on how clear the person was that was actually drawing or writing it out, you could say, sort of like there's a space here, that this one is in the 60s place and this one is the ones place, and it could be a 61. Right? It might be. Or what we think it is that it's actually the number 120. And that's what it was supposed to be. It was supposed to be 2 60s, right? A triangle worth of 60s each time. Now, it says this value, it's talking about the original value. Looking back at our original value, what did we have? So let's talk about how we would convert it if we were just given the problem to begin with, convert this value. So over here, let me clear off what I had here. You need to know where you decide to break up place values, right? Because it kind of all looks like it's mushed together. Now, sometimes when your book does it, it'll look like there's a space between them, and obviously if they put a space in there, they're intending to show you that there's a break. Make sense? If there's not a space indicated, we will assume that the spaces are only where a small value hits a big one. So the triangle is worth less than the arrow, correct? So the triangle worth 1 coming before the arrow worth 10 is a natural break where there has to be a break in the number system. Okay, there has to be a break in the place values. Now, there's no indication to us by a space or anything else that there's any other breaks, because the 10s now come before 1s over here. Okay? So bigger place value before smaller ones, or bigger numeral, that's what I'm going to say. Bigger numeral before a smaller one was within 1 place value. So this value is worth 1. How much is over here if I have 5 arrows and 9 triangles? That's 59. Okay, so I'm going to move over to the slide to write those down. I have a 1 here, and I have a 59 here in value. But this is the 1's place, and this is the 60's place, and of course if we had a third one we'd have 60 squared and so forth. We don't have this. So what do we really have? Well, we have 160, it's like having a $60 bill if you want, and then you have 59 $1 bills for a grand total of $119. That's the original value that I was given, is 119. Okay? So obviously the number after should be 120, but there's really not a way in their number system to write that with absolute certainty that that's the number we mean, because there's no place value holder in their system. They're missing a 0, right? Yeah, not so cool. All right, let's go the other direction now. We're going to take one of our numbers. It's the same one we actually did for the Egyptians before. And we're going to, I think it is. Oh, it's close. It's not the same. It's close. And we're going to turn it into their number system. So the number is 43,205. Okay. Now, the process to turn it into our number, or our number into their number, is also more complicated than the Babylonians. The Egyptians. The Babylonians are more complicated. Egyptians was real easy. We said, oh, there's 4 10,000s, there's 3,000s, and we just wrote the symbols down, right? But they didn't have this place value system to contend with. So let's see what we would do. What we're going to do is we're going to take this value and we're going to consider the place values in their system. They had a 1's place. We already mentioned they had, oops, I meant to put it underneath it. The 1's place, they had the 60's place, they had 60 squared. What is 60 squared? 3,600. And then they had a 60 cubed place. What is 60 cubed? 216,000, and that is bigger than the number that we are given, correct? Our number is only 43,000. So I don't need to worry about any other powers of 60 because 60 cubed is already too big. So far, so good? my place value on this number will have, or my number, numeral on this number will have 3 place values. It will have a 60 squares place, a 60s place, and a 1s place. Okay? So here's how you do this. Your book does something that's absolutely fantastic on this. I call it division scaffolding. I don't know if they called it that or if I just made that up, but that's what it looks like to me. So a division scaffolding means that the biggest number in our place value system is going to go on the outside. That was 3,600. And we're going to do like a division bar that looks more like a top hat. Or like a reverse hole in the ground or something like that, upside down hole. Underneath this top hat is going to be the number that we're trying to change, 43,205. So what we're really trying to figure out is how many 3600s are there in 43,205. So this is where I said your calculator is going to be super handy today. So take 43,205 and divide it by 3,600. And I want to know how many holes go in. I don't want the decimals. I just want to know the whole number parts. 12. All right, now take your calculator and do 12 times 3,600. $43,200. So a visual picture of what we just did is somebody came in. We're almost to Easter. We're close enough that I'm going to use this example. Somebody came in and they dumped 43,205 jelly beans on the floor. That's a lot of jelly beans, right? And you came in and you put them in piles of 3,600. There are 12 piles of 3,600 across our room. And then, because we know that that's 43,205, you can also tell me that there are 5 left over. Little lonesome jive jelly beans.
Yeah, again, you multiply 12 by...
3,600.
Okay, I got 43,205.
You got 43,000 what?
205?
Try again.
Okay.
12 times 3,600 can't give you 5 on the end.
Okay. I guess I was using the decimal.
Maybe so.
So you
Yeah, yes,
have
you
to
probably
add
did.
the one.
Yeah, it's just the
Okay.
multiply. It's just the whole number part that you're
Okay.
multiplying. Yes, good question. So we have 5 left over. Now, in order to make sure that we catch all the values correctly, we're going to do our next value, which I know it's not going to go in, but it's the 60s place. And we're going to say that 5 will not go into 60, it'll go in 0 times. It won't go in at all. And technically then 0 times 60 is 0. And we still have the 5 left over. So we're just going down in place value. So we did the 60 squareds place, we did the 60s place, and now we're going to do the 1s place. 5 goes into 1 5 times. 5 times 1 is 5. And I have 0 left over. Okay? So this is the point when I'm done because I had 0 left over and because the last place I've divided by was the 1s place. Okay? So the answer that I have, if you think about it in terms of these numbers over here, is that I have 5 1s, I have 0 60s, and I have 12 60 squareds. But now I'm going to write it with their numerals. How do I write a 12 with the triangles and arrows?
One triangle and 2
One triangle and 2
arrows.
arrows. I think you got it backwards.
Actually, yeah, that's right.
Yeah, 1 arrow and 2 triangles.
Yes.
Yeah. So 1 arrow, and the arrow's worth 10, so it comes first. An arrow's worth 10, triangle's worth 1. So arrow comes first, and then 2 triangles. And this is the number 12 in their system. If they had a place value holder, we would put it next, right, to represent the 0. No such thing happens, because it's not one. You can leave a space, but I don't know how you would leave a space big enough to indicate that it's actually got 0 in a 60 spot. However, there is a 5 that you have to include next, so you can leave a space here like this to indicate that it switched to some other place value. But as you can imagine, looking at this, it still looks like it might be 12 60s and 5 1s. Yes? And that's just the unfortunate nature of the Babylonian system and probably in great part why we don't use it today. There's a problem with this system, right? Inherently flawed. All right, you ready to learn about the Mayans? The Mayans are quite unique. They only have 3 symbols. A dot, a line, and it looks kind of like a shell. The last one, right? I think it's sometimes called a clam. The dot is worth 1. The line is worth 5. And the clam is worth 0. And we all said, oh, that's good. There's a 0. We should, because that was definitely a problem in our last system, right? But let's also remember that the Mayans predicted the end of the world in 2012. And last I checked, we're not in 2012, folks, right? We continued beyond those Mayans. So there must be something else going on here that's probably not why we, or probably why we don't use their system. They do have a place value system. It is a modified base 20 system. I'll tell you about the modification here in a minute. It is written vertically. That's different. And we always put dots above bars. Okay, so if you had the value 6, you'd put a dot on top of a line. Make sense? That would be right how you would write that. Okay, so we know what a base 10 system is. That's what we have. We've talked about what a base 60 system looks like. It's powers of 60. If this were a base 20 system, it would be powers of 20. Now, because it's written vertically, the smallest value is on bottom. So this is the ones place. That's a bad looking one. That's better. And then they do have a 20s place next. And I'm not drawing lines to these to indicate their value 5. It's just a placeholder line like I drew on the last slides, okay? So there's some kind of value in that. The next value above the 20s value is not 20 squared. This is where the modification comes in. It's actually 20 times 18. And if you will, grab your calculator and tell me what 20 times 18 is, and we'll talk about why they did this. 360. So tell me what you know about the 360 and why they might have liked that number better than, say, 400, which would be 20 times 20.
Just 360, or almost 360 days in a year.
Yes, and that's the reason. The 360, give or take, days in a year. Okay? Where else have you seen 360 just for the sake of argument? Degrees in a circle, yes. So there's something that's sort of naturally appealing about this number 360. So they wanted a place value that had 360 in it. Okay? After we get past this sort of odd number right here, what we do is we then square the 20 times our 18. And we would then cube our 20 times our 18 and so forth. So there's just always this awkward 18 hanging on there, but the powers of 20 then increase as we go up. Okay, now we're going to need these later, so let's go ahead and write these down. I have the 360 here. What is 360 times 20, or 20 squared times 18? What do I get for the next one? 7,200. And what was our next one above that? Okay, and I think that'll be enough for our problem, so I'll pause right there. So their place value system goes 1, 20, 360, 7,200, 144,000. The other one, the Babylonians went 1, 60, 3,600, and then, man, what was the next one? 216,000? Where was it? Oh, there it is over here on this one. Yep, 216,000. Now, when it comes to thinking about these number systems for your test, I mentioned before, you do not need to memorize the symbols themselves. But you do need to remember or write down properties of them, because that's not on this paper that I've got. You need to know that the place values are from smallest to largest, you know, on the bottom to the top of the Mayans. You do need to know that it has this modified base 20 and what those powers are. Whatever those kind of structural things are, that's not on your note card. It's just the symbols themselves. Okay? Okay, so let's look at the Mayans. We have this value, 2 dots in a line, 3 dots in a line, and I told you just a moment ago that dots come above lines. So this is one place value, and this is a second place value. Okay, the dot connects to the line beneath it, they're attached. And if there's like 2 lines, then the dot connects to the 2 lines beneath them, they're attached. Okay, so if we're, oh my goodness, what did I do? There we go. So if we're counting here, the red that I've highlighted, how much is that? 7, because it's 2 dots and a line. Dots are worth 1, lines are worth 5. How about the yellow highlighting? That's 9. Everybody good with that? There's 7 in one place, 9 in the other. This is not the value 79 though, agreed? Because it's not our base 10 system. We'll get to what the value is in a minute, but let's answer the questions as they come. The first issue says, what Mayan numeral comes before this value? Well, the smallest place value is on bottom. So what would I have to do in order to show that I'm going to decrease this value by 1? Take away a dot. Good job. So the 2 dots and line on top, they stay. Dot, dot, line. But instead of 4 dots down here, I only have 3 dots and a line. I just remove a dot. Because a dot's worth 1, and I remove it in the lowest part of the value. That's our ones place. So what would I then do in order to show that I need to increase it by 1? Add a dot. But what happens on this number if I add a dot? It becomes a line. So again, the values at the top on this one aren't going to manipulate. They stay the same. But on the bottom, instead of having any more dots, I have 2 lines. And can you see that there's already a problem? Or at least a potential problem with this. I tried to sort of put a space in there, but it could look like there's not one, right? It could. And so this number might actually be interpreted as though I had dot, dot, 3 lines, and this would be the number what? 17. In the ones place. Yeah, it could. It wasn't supposed to be 17 in the ones place, right? It was supposed to be 7 in the 20s place. And what did I have? 10 now. Yeah, 7 in the 20s place and 10 in the ones place. That's what it was supposed to be. This value right here was supposed to be 7 in the 20s place and 10 in the ones place. That's what it was supposed to be. But it's really difficult to make sure that that's interpreted properly. Now let's actually figure out what the original number should have been interpreted to be. So we had written down that it was dot, dot, line was 7, 4 dots, and a line was 9. So I have, the way this is done is that I have the ones place and I have the 20s place. I have 9 in the ones place and 7 in the 20s place. Or you know what, let me write it this way. The way I just did on the last slide. 7 in the 20s place, 1 in the 9s place. So what is 7 times 20? Think dollar bills if you only had, yep, that's 140, right? And then 9 times 1? 9. And you add them together, you get 149. That's what the original value is. All right, so what would we do if we wanted to write their number from our value? So our value is 58,532. And we want to write it in Mayan. Okay, well what do? Well, we do the same division algorithm that we had before. Now we had already written these down, that we had the 144,000s place, we had the 7,200s place, we had the, what was next? Oh, did I write 360? Did it go to 7,200 or am I missing that?
No, it goes to 7,200 because you got the 20 square and then times that by 18 to get 7,200, I think.
It's not at 7,200. I've got a symbol wrong. Double check with me. If I have 360, what's 360 times 20?
72.
Yeah, 7,200. So maybe, is it 144,000 if I multiply by 20 again?
Yeah.
Okay. So I have 7,236, 360, and then I have 20 and 1. Does that look right to you guys? That's what I've written down. Okay, fantastic. All right, so we're going to divide by the biggest value that actually will divide into 58,000, which is not going to be the 144. Agreed? Yeah, I don't need that one. But do I need the 7,200? Yes. So we're going to take 7,200 on the outside of our algorithm, and we're going to write the 58,532 on the underneath. All right, whole numbers is what we're looking for. Take 58,532 and divide by 7,200, and I want to know how many whole number times it goes in. And the number, sorry, what was it, Catherine?
8.
8. If you get a number in this system that is 20 or bigger, you've got a problem. because they have a base 20 system, right? Each place value can only have 20 inside of it. You can't have more than 20 in there. So if you divide this and you got 20 on this, it meant that you probably should have divided by something bigger to start with. You didn't divide by something big enough. All right, now what is 8 times 7,200? 600 what?
600.
Even? Awesome. 57,600, and then we subtract. So what do you get when you subtract these? 932. So we divided by 7,200, now we're at 360. So we're going down in place value. How many 360s are there in 932? 2. What is 2 times 360? 720. And if I subtract, what do I get? 212. Okay, moving down in place value, I now have the 20s place. So how many 20s go into 212? 10. 10 times 20 is 200. 212 minus 200 would be 12. Our last step is to divide by 1. There are 12 12s in the number 1. There are 12 ones in the number 12. I said it backwards. There are 12 ones in the number 12. So 12 times 1 is 12, giving me a remainder of 0. That tells me I'm done. Whoops. Because I divided by the number 1 and I got 0 in the end and I'm finished. These digits then are the ones that I need. I have 8, 2, 10, and 12, and they're all smaller than 20, right? So we didn't make that mistake. No, I mean, we could have made some other mistake, but we didn't make that mistake anyway. The numbers are the right size of numbers. So we're going to go then with the number, and we're going to write how we write it in their system. How do I write an 8 in Mayan? A line and the 3 dots, and the 3 dots go on top of the line. That's 8. How do I write a 2 in Mayan? 2 dots. How do I write a 10 in Mayan? 2 lines. And do you see a problem? Yeah, because those 2 dots certainly look like they could somehow be connected to the 2 lines, right? How do I write a 12 in Mayan? 2 dots and 2 lines that look a lot like the 2 dots and 2 lines above them. And unfortunately, even though we have a 0, we've still got some problems, right? Yeah. Now, the problem that we wouldn't have is, let's say, for instance, in this division over here, right in here, we ended up with a 0. That's actually okay in this number system, because what would we do to represent a 0? We draw one of those shells, right? So we'd be cool with a 0. That's not the problem. The problem is somehow combining these to make a dot and a line combined to look like they're attached when they're not, or vice versa, right? That's the problem. All right. Last one. We're going to talk about the number system briefly. We won't get all the way through with this one. And I have a job for you to do when you leave, even though it's not homework. So, you've seen these ones before, right? The Romans? Okay, so write them in first. I, V, X, L, C, D, M. And then let's talk about where you've seen them before. Where have you seen in real life every day right now, maybe not every day, but you've seen them on a regular occurrence, so to speak, Roman numerals? Super Bowl. What?
Music theory.
Music theory. That might be the first time anybody's ever said that one for me, Beth. Thank you. Music theory. Cool. What else? Civ class, in terms of what? Where have you seen them in Civ?
Like moving the 16.
Okay, so suffixes on names, right? There's the subscript after them. Okay, what else?
Some clock faces still use Roman.
Some clock faces will use them.
So,
Outlines, that's the one people usually tell me. Outlines, that's what I thought you were going to when you were talking about Civ, so you probably saw an outline in Civ. Any others?
usually any kind of like handbook, like a teacher or student handbook.
Yeah, teacher-student handbook, and they're using it in an outline form usually, right? Good. Sometimes you'll see them on chapters in books, like especially if you're doing something that's an older classic book. I'm thinking like Wuthering Heights, Jane Eyre, that kind of stuff, Tale of Two Cities. They'll number their chapters with Roman numerals. Another place I've seen them is if you travel to the East Coast. Sometimes you'll see them as establishment dates upon buildings. You guys know what I'm talking about? I mean, like, because that's where the country began, was over on the East Coast, yeah, and at least in terms of Western culture. So you'll see them on establishment dates on buildings. Let's write our values in. What's the first one's value? 1. How about the V?
5,
Good. X?
10,
L?
50,
Good, 50. C? 100. There's fewer, like, sure sounding, like, I know this one kind of answers. Okay, what do you suppose D is based on the pattern you're seeing?
500,
Yeah, it's 500. And the M?
1,000.
1,000. Okay, now you might look at this and think, okay, that's all the ones we're going to write down. And it is. These are all the symbols. So what would you do if you needed, say, 100,000? Because I don't know about you, but I'm not going to write 100 M's. Agreed? So anything that's bigger than this has a different way to represent it. That's actually one of the facts, the properties we're going to look at, is what happens with bigger numbers. The other fact is that they're not going to do like the Egyptians did, where they wrote out 9 heel bones, right? They have a subtraction property that you're probably familiar with as well, and we're going to talk about next time how that subtraction property works. So here's your homework. You guys ready? It's not really homework you have to bring in, but it's something I do want you to do as you're walking across campus. I want you to look at the clock on Rayleigh Chapel. And when you come back next time, don't talk to each other and be like, don't cheat. This is no fun if you cheat. See if you can figure out what is wrong with the clock on Rayleigh Chapel. And if you already know it, mum's the word until I see you next time, okay? What is wrong with the clock on Rayleigh Chapel?